Today I would like to present a small talk about variance measurements, particularly the uncertainties, and I will present a Bayesian approach, which is the approach that I have used during many years. And I have subtitled this talk, Why the Error Bars Are Longer Upward Than Downward. So you remember that my last talk was about Allen variance and friends, and the next one will be devoted to cross spectra and Gros-Lambert covariance, I mean tricorner hat and so on. And I will finish with holdover and long time extrapolation. Okay, so today I will discuss about the distinction between the model world and the measure world. I will explain a bit something that you perhaps know or heard about, which are the chi-square distribution. And I will give a little focus on chi-square distribution in order to be sure that everyone understands exactly what it is. And I will describe the Bayesian approach, which is the heart of my talk. And after that, I will use it with an example with a chi-square distribution with 2 degrees of freedom, and I will try to generalize to every law that we can encounter during your measurement process. And I will finally ask the question, is it better to use variance or deviation, as usual, and I will conclude. So first, I would like to go back 2,500 years before. I was not born at this time, but there was a guy who was called Plato, and Plato's idealism, you heard about it, I think, during your philosophy lecture in high school, perhaps. For Plato, what we see about the world, what we feel about the world, what our sense gives us as an information of the world, are not the world. The world is perfect, and what we have, the information we get, are not perfect. It's you know the allegory of the cave. You don't see exactly what is. You see only a shadow, which is a reflect of the reality, but it's not reality. For instance, for Plato, a true circle is something which is an ideal one, which is given by this equation, for instance, and with our sense we see something like that, which seems more or less like a potato and not a circle. And we are still in the same paradigm, because when you say we are working on a model, in a sense, generally, we consider that there is an equation, and this equation is very accurate. You have numbers. If you know perfectly time, you know perfectly the model parameter, you know exactly what is, in the example of the falling body, for instance, you know exactly what is the elevation and the duration of the fall and so on. And the model parameter is a true value, it's a true number, and that's it. And sometimes students who are undergraduates, they say it's much more precise to make a theory than experiment, because experiment, it's always false and so on. But yes, but this is the measure world, and the measure world is like that. Each time you want to measure something, you have to deal with an uncertainty. Here you have the uncertainty in time, you have the uncertainty about the elevation of the falling body, and of course, it gives you an uncertainty on the model parameter, which is a function of the uncertainty of time and uncertainty of elevation, and we are obliged to deal with that. But of course, the temptation is great to go to the model parameter, because we can do many things, as said Eugene Wigner, thanks to the unreasonable effectiveness of mathematics. So let's go to the talk itself. I will begin by a citation of my colleague Eric, who is here. It's the first sentence of his lecture in statistics. Let theta be an unknown parameter, it will remain so. So we have to admit that we will never know what is really the parameter. But it's possible to have an idea of it, of course. So in order to do that, we will distinguish, as Plato, the model world and the measure world. In the model world, we have, if we deal with Allen variance, for instance, you have the algorithm of the Allen variance, But the algorithm of the Allen variance will use a mathematical expectation, and mathematical expectation is something which is in the model world because we can't have access to it, to the result of it, because it involves an infinite average. Of course, it's not possible in the true life to make an infinite average. So it's not possible to have the real value of the Allen variance, but we imagine that it's a pure number which will characterize perfectly an oscillator, for instance, for this time. In the measure world, we consider that we can estimate the Allen variance, and I will use the same algorithm, but it's finite, of course, and you have only n values and not an infinity of them, and this will introduce some fluctuation, but the difference is the fact that we perfectly know the measurement, but we don't know the parameter. On the other hand, the measurement in the model world is a random variable, and we know the parameter. You see the difference between these two worlds. We have to try to go from one world to the other one. So I will take a statistical model, and I will try to follow with this statistical model, which is very simple. I took the most simple statistical models that was possible. You have here a measurement, and this measurement is equal to the parameter which is here, but there is a random variable which is here, and you see that the random part of this measurement is concentrated in this term here. I will detail a little bit later what does this mean, what is a chi-square divided by nu and so on. But what we have to know just now is the fact that the mathematical expectation of this random part should be equal to 1. In another word, if you make an average of xi, it should tend toward theta. And if you take, of course, the mathematical expectation, but you know that mathematical expectation is not in this world, you will find theta, so it means that it's an unbiased estimator. Okay? I ask you if you have something which is difficult, you raise your hand. Don't hesitate to raise your hand. I will try to explain by other words if there is a problem. Okay, it works. So xi is a measurement. This symbol here, and from this measurement we will try to have an estimate hat theta of the parameter theta. This is all what we can do. Of course, hat theta is the random variable which is in the measure world. I will explain later that chi-square nu is a pure chi-square distribution with new degrees of freedom, and nu is smaller than n, which is the number of operands that you have in this measure. What I must highlight is the fact that nu in my talk is not a frequency, it's the numbers of degrees of freedom, and all along my talk it will be a number of degrees of freedom. Okay, so I will begin by a well-known distribution, which is a Gaussian distribution. I think everybody knows what Gaussian distribution is. I will take a random variable x, which is a centered standard normal random variable. What does it mean? Centered, it means that its mathematical expectation is average, is means, if you want, is equal to 0. Standard, it means that its variance is equal to 1. Normal, it means that it's a Gaussian distribution. This symbol stands for variance. When I put some double bar like that, this is a mathematical expectation, this is variance. I think that I will no longer use this one during this talk. So if you plot a sequence of Gaussian distribution, you have something which is like that. We have 0, which is here. Since we have centered, all the samples are dispersed around 0. Sometimes they go a little bit further, but you know the Gaussian distribution, it's not possible to, it's very improbable to have a sample which is at 100 or 1000. It's not impossible. The probability density function is not null, but it's very, very, very rare. Okay, So that's it for the Gaussian sample. So what is a chi-square distribution? A chi-square distribution is nothing but the square of a Gaussian random variable. If you make the square of one Gaussian random variable, you have a chi-square distribution with 1 degree of freedom. And if you take the square of new Gaussian random variable to the square, you have a chi-square distribution with new degrees of freedom, which is generally denoted as chi-square underscore new. It's written here, sorry, but I go a little bit too fast. I will not demonstrate that, but you have to know that the mathematical expectation of a chi-square distribution equal to nu, equal to the number of degrees of freedom, and its variance is equal to 2 nu. I will not demonstrate that, but anyway, we will use it. So if we look at an example of chi-square distribution, in this case, there are chi-square distribution with 2 degrees of freedom. It looks like that. So you see that, of course, it's always positive because you have a square. So it's not possible to have a negative. It's impossible to have a negative sample. But you see that they can go very to very high value. Here you have several values which are over 10, whereas the average is 2. So it's a completely different distribution. So I switch the chi-square here in order to go to the thing which characterize the chi-square distribution, which characterize all distribution. It is a probability density function. Everybody is okay with a probability density function? Just in a few words, it means that if you have a function, if you integrate this function up to x, for instance, you have the probability of a value to be smaller than x. That's it. So if you have a chi-square distribution with new degrees of freedom, the probability density function look like that. So you have here for several numbers of degrees of freedom. And what is interesting to see is the fact that if the number of degrees of freedom is relatively high, for instance with nu equal 10, you have something which begins at 0 here, and which increase and decrease. And it looks a little bit like a Gaussian. If you have a large number of degrees of freedom, you can consider that your data are Gaussian. But if there is a small number of degrees of freedom, it's not at all Gaussian, because you have, as you said, as you have seen here, you have this one is with 2 degrees of freedom, is the red curve. It is maximum at 0 and it decreases as an exponential along this axis. So if we look at nu is the equivalent degrees of freedom, yes, it's important to precise this point. Equivalent, it means that it's not mandatory an integer. It can be a real number, because sometimes you can imagine that nu is not exactly equal to an integer. It could be equal to 2.5 or something like that. And we will see why is it possible to do that. Of course, if you take this definition, it's not possible to have a summation which is not an integer, but we can admit that it could be integer if there are correlation. We will see that later on. If we take the example of nu equal 2, we obtain this PDF, this probability density function, which is, as I said, a decreasing exponential. And if I perform here the histogram of this data, I obtain this. And you see that this is perfectly in very good agreement with the probability density function. So in order to simplify, the probability density function is a little bit like an histogram with a very small width bar in the histogram. Okay, this is represented in the as a linear graph, but sometimes, particularly for the type of variable which are, you see that there are a lot of samples which are close to 0. It's interesting to see what happens if you look at a semi-log graph. And in this case, you see that on a semi-log, you have a distribution which is quite different, because now you see that there are very few of data which are below 10 to the minus 2, and you still see that there are very few data above 10, and most of them are between, let's say, 10 and 0.1. And it's possible also to represent the corresponding PDF here, and you see that you have something which is with a maximum which is equal to the number of degrees of freedom, which is 2 here, and which has which cuts relatively quickly here because we have something which is exponential, but a very long tail here because it decreases very slowly. Okay, so how is it possible, because we will see that it's very important, how is it possible to estimate the equivalent degrees of freedom, because it will be very important. You saw that the power density function, is given versus the equivalent degrees of freedom, so it's very important to do that. So first of all, we can see that here we have two Gaussian samples. The difference between two Gaussian samples is a Gaussian sample, a Gaussian random variable, centered and so on. If you take the square, you have a chi-square distribution with 1 degree of freedom, and if you take the sum of n of them, you should have a chi-square distribution with n degrees of freedom. But it's true only if your samples are uncorrelated. And you know that if you do Allen variance, there are two problems which will arise. The first one is the fact that if you have to deal with a low frequency noise, I mean a flicker frequency noise or random walk frequency noise, the samples are intrinsically correlated. So they are not uncorrelated. Moreover, we use generally overlapping variances, and overlapping, you know, it introduces some correlation. So the number of degrees of freedom is not equal to the number of operands which is here. It's smaller, and it's necessary to try to estimate what is this equivalent degrees of freedom. How to do that? My advice is to use a paper which has been written by Chuck Greenall and Bill Riley in 2003. It's a conference paper. I don't know why it never have been published in a journal, but that's another problem. But it's really a recipe which is very precise. You have directly the algorithm. You put the ingredients, the inputs. The inputs are the value of tau, the value of the sampling time, the type of noise which is dominating, and you get the result. You just have to make the calculation. So it's relatively easy to know what is numbers of degrees of freedom corresponding to one calculation of the Allen variance. Now I would like to present you a graph which is an illustration of my statistical models that I presented previously, in which we have the measurement xi, which is equal to the parameter theta, multiplied by the random part, which is this random variable, which is a pure chi-square distribution. In my example, is still with 2 degrees of freedom. If I vary theta from 10 to the minus 2 to 10 to the 6, I observe this sort of graph. So for each theta, I will say if theta is equal to 1, for instance, and here it means if I say that theta is equal to 1, it means that I am in the model world, because I know the value of the parameter, the model parameter. If I know the model parameter, I'm not in the world of the measure. So I look at this model parameter, which is equal to 1, and I see this distribution, and this distribution are all the possible xi measurements which are compatible with theta equal 1. If the parameter is equal to 1, I can observe all these measurements from, let's say, 10 to the minus little bit, 10 to the minus 3 to 10 approximately. This is what we call the direct problem. From the parameter, you obtain the measurement. But it's not what we do generally. Generally, what we do is to have the measurement, and from the measurement, you want to know what is the parameter, the model parameter. So this direct problem is not useful if you want to make a parameter estimation. It's only useful for guys like me who would like to make simulations. If you want to simulate a measurement, for instance, you can use this sort of model and you will have directly the behavior of the measurement and so on, knowing the type of random variable that you have that you expect. Now, I would like to see the same result. I will perhaps detail a little bit. Yes, if I make a zoom on this part here, we obtain this. So you have now the parameter which is equal to 1, approximately, because you see it goes from 0.5 to 1.05, and you observe that you will still have the same behavior that previously with my first example, so except that you have more samples. Here we have a little bit more than 20,000 samples, I think. And if we do the histogram, you observe that you have this type of histogram, and this is exactly conform in good agreement with the theoretical PDF of the chi-square distribution with 2 degrees of freedom. So no surprise, it's what we expect. But now, if we look at this graph, but in the measure world. In the measure world, it means that you have performed a measurement, and you see that this measurement is equal to 1, for instance. So it means that you are looking in this direction. If you look in this direction, you are in the measure world. And you look in this direction, and you know that your measurement is equal to 1, and you have the possibility to observe all the possible model parameter which yields a measurement which is equal to 1. This is really what is interesting for us, because it's really the process we have performed. We know the measurement because we got it during the measurement process. And so it's the so-called inverse problem, and you have to try to estimate, to assess what is the model parameter knowing this measurement. So this is what we have to solve to perform an estimation of theta, and we will have hat theta in this case. If we look a little bit more in detail to this part, I look and zoom of this part here. We have this distribution, and you see that this distribution is quite different from the previous one because it's inversed. You remember the previous distribution? I can go back to it. Yes, you have to. I can change, but I can't turn my the screen. You see that. Sorry. You see that at the beginning we have a shape which a tail, a very long tail for the low value here, and a sharp cut here, approximately at 10. Now, if you look in the measure world, you have the opposite. You have a relatively short cut at the beginning here, at 10 to the minus 1, and you see that you have a very long tail up to value very large. So it means that if you look at the data, you see that effectively you have samples which are very far from the center. The center is approximately equal to 1, and you have value up to a few thousands. So you have a parameter which is equal to 1, and a measurement which is equal to 1, and you observe that this measurement is due to a coefficient which is approximately equal to 1,000, for instance. It's possible. It's not very frequent, but it's possible. So you have to take that into account. So theta, hat theta, will be the random variable which will describe the probability density function of this estimator. We will have an estimator of theta, hat theta. Hat theta is obviously in the measure world, and you have to use it in order to know very well what is the confidence interval around the parameter theta. So it means that if you know the PDF of this variable, this random variable, you will be able to, for instance, calculate the mean estimate. Mean estimate is always given by this sort of calculation, and you will be able to measure what are the bonds to 5%, for example, and the limit at 97.5% in order to see what is the center, the error bar at 95%. Right? It's very useful if you want to make error bars, in other words. I focus a little bit on this quantity, which is here, which is, perhaps I forgot to mention the other one, which is in the, no, it was not written here. So it's the first time it appears. Okay. Here, it's the slash, not the slash, the vertical bar, which is here, means knowing the quantity which is behind. It means here what is the PDF of the estimate theta, knowing the measurement xi. When I say measurement, it could be a plural. We could have several measurements. We will take into account all the measurements we have, and from all these measurements, which are known because we have measured them, we will try to infer what is the parameter estimate, which is hat theta. So we will have error bars around this value. Okay, so this is the point where we will need the Bayes theorem. Remember what we said. We know the PDF of the measurement knowing the model parameter. I call it P of xi, the measurement knowing theta, the parameter. In other words, is the distribution of your measurement. You see that your measurements are Gaussian or chi-square distributed and so on. And you can deduce from that what is the distribution of the parameter estimate knowing the measurement you performed. Okay? It exists a theorem which has been invented for another reason. It was nothing to do with that. I think that Thomas Bayes in the late 20th century wanted to demonstrate the existence of God by probability. I'm not sure that he succeeded, but it's another story. And what is very interesting in this case is the fact that in this book, there is a conditional probability. I forgot to mention, when you have a probability knowing something, it's called a conditional probability. And he says if there are two events, A and B, the probability of B should be different from 0 because we will have to divide by it. So it's for mathematical reason. The probability of A knowing B is equal to the probability of B knowing A multiplied by the probability of A divided by the probability of B. When we say that, it's a little bit difficult, but I will explain that with a very simple example. Imagine that you have a bag. You don't see what is inside the bag. This is a cut in order to understand what happens. In this bag, there are 3 red balls and 2 blue balls. You see the red balls are here, the blue balls are there. The event A is the probability to... A is a red ball has been drawn. B, a blue ball has been drawn. So we can imagine what is the probability to draw a red ball knowing that a blue ball has been drawn. This is P of A knowing B. I will try to explain that. What is the probability of draw a red ball? P of A, you see that there are 3 red balls among 5 balls, so it's a probability, obviously, is 3 over 5. What is the probability to draw a blue ball? There are 2 blue balls into 5 balls, so it's 2 over 5. Now, what is the probability? And look at that. What is the probability of drawing a blue ball knowing that a red ball has been drawn? You see that one of the red balls has disappeared here. So you have no longer 5, but 4 balls. And among these 4 balls, 2 of them are blue. So the probability is 1 over 2. And now we can also estimate what is the probability of draw a red ball, knowing that a blue ball has been known. Okay, here, one of the blue ball has been removed, so it remains only 1 blue ball and 3 ball red. So the probability is 3 over 4. But we can see that if we apply the Bayes theorem, you have exactly probability of B knowing A, 1/2, multiplied by probability of A, which is 3/5, divided by probability of B, which is 2/5. So you can simplify by 5 here, and you can put the 2 below, and you have 3/4 is equal to this one. So it's not a mathematical verification, of course, but it proves that it's true. It works. So what is the interest for our purpose? The Bayesian inference, not interference, sorry. The Bayesian inference gives way to compute the PDF of the parameter estimate knowing the measurement. And you estimate it from the PDF of the measurement knowing the model parameter. And you just have to apply the Bayes theorem. What we are interested in is the probability of the estimate parameter theta knowing the measurement. So it's equal to the probability of the measurement knowing theta. You know it because it's a Gaussian, d squared, and so on. Multiplied by the probability of theta without measurement, a little bit strange, but, and divided by the probability of the measurement without parameter. It's a little bit more difficult to understand what it needs, but we will try to deal with. And we have the general property of all PDF, all probability density function. Of course, you remember that it gives you the probability for a number to be below the value which is given here. If you have infinity, you are sure that you will have any value which will be below infinity. So the probability when it tends toward infinity is equal to 1, of course. So it gives a possibility to normalize that. So first of all, what is the probability of measurement, whatever the parameter? We don't care because it doesn't depend on theta. The variable for us is theta. So we don't care of it. We can consider that it's constant because it doesn't depend on theta. So we can imagine that it is equal to k. And if we use this property, you replace p de theta knowing xi by that, and you see that you can take out the probability of xi, and you can take out the 1/k because it's a constant. So it will be determined later on. So what is the probability of hat theta? It's the probability of the parameter estimate before any measurement. So it means it's a priori knowledge of theta, which is denoted generally p de theta. This is really the originality of this method, because we are obliged to imagine what we know about theta before to measure it. Sometimes we know nothing, sometimes we have small ideas, sometimes we have... So we have to take into account all what we can do, but in this example, I will give an example of total ignorance and what is a good parameter, a good model for total ignorance. It's a good question, I think. So I will try to do that. I will define a prior, which is a prior of total ignorance, and knowing that, I will imagine that we have directly here the probability of the estimate, the parameter estimate, knowing the measurements eventually. And it's possible to know this constant because you know that all that is normalized. So what could be a prior of total ignorance? Total ignorance, it means that you have absolutely no knowledge about theta. When I say no knowledge, it means we don't ever know what is the order of magnitude. We don't know if it's about 10 to the minus 43 or 10 to the 24, for instance. We don't know. So we should have a prior which will reflect this total ignorance. First of all, we can imagine that you have a prior which is constant, because you have the same probability for any value. But imagine that if you have, you would like to know what is the probability for the parameter to be within an interval very small, for instance, between 10 to the minus 18 and 10 to the minus 17. If you make the computation, you integrate and so on, you have something which is about 10 to the minus 17. What is the probability to have another order of magnitude, which is, for instance, between 10 to the 23 and 10 to the 24? Here you can make the same calculation and you have something which is about 10 to the minus 24. So you see that we have, for two different orders of magnitude, but we have the same width, you multiply by 10, you have completely different probabilities. So it means that if you choose this prior, you will privilegiate all the high values and you will completely forget all the small values. So it's not at all suitable to be a prior in our project. On the other hand, if we use this type of prior, and in this case you have something which decreases with theta, what happens if we do the same exercise? You imagine that what is the probability of theta to be within 10 to the minus 18 and 10 to the minus 17, and you observe that doing that if you integrate the 1 over theta, you have a log, and the log, if you do that, you can imagine that it's log 10 to the minus 17 divided by 10 to the minus plus in the inverse 18. It means that you have k log of 10. And if you do that with a very huge order of magnitude, it's the same, you have k log of 10. So it means that you have the same probability, whatever the order of magnitude is. So it means that you really have the constant prior. I think it was a copier-coller, comme on dit, of the previous slides. Anyway, it's not a constant. The 1 over theta prior doesn't depend on the order of magnitude, so it's suitable. It's a suitable prior for what we have to do. There are more sophisticated priors. One of those who is most used is the Jeffreys prior. Jeffreys prior is the 1 over the I don't remember, it's not a problem. Now we are able to go to the posterior. When I say posterior, it's by opposition to prior, it's the probability of, to know what is the probability of the model parameter estimate knowing the measurement. So I go back to the algorithm in the model world and in the measure world. Theta is a pure number, but we have to deal with and the statistical model was this one. So you remember that we have the probability of the measurement knowing the parameter which was given by this exponential, this decreasing exponential, with of course this quantity. In this case, because we have this model, it gives this normalization. And now we are able to build the probability of the parameter estimate knowing the measurement, which is here. And we have 1 over theta multiplied by this quantity. And we have to normalize. In the case of nu equal 2, we obtain this quantity, this function. And remember that in this function, xi is no longer the variable. Here xi is the variable, but here the variable is theta, and xi is one of the parameters of the model. Okay. So we have now the PDF of the model parameter theta, knowing the measurement xi. What can we do with that? With that, we have to obtain a confidence interval around the model parameter theta from this PDF. Example, if you want a 95% confidence interval around the estimate hat theta. We consider that hat theta, we will give more, no, it will be more precise in the other sense. We consider that the measurement we got is a good estimate of the model parameter theta. So we will consider that hat theta is equal to xi. But what is important is not that. What is important is the uncertainty that we have above. What is the confidence interval in which you can say that? You have to send, if you take, if you choose a 95% confidence interval, you have to eliminate the first 2.5%, which goes from 0 to the first bound, the bound at 2.5%, and you have to eliminate the last part. Perhaps it's easier to see that on a graph. You have to eliminate this part and to eliminate this part. So it means if you want to keep 95%, you have a bound which is the limit, inferior limit, which is at 2.5%, and the upper bound, which is the limit at 97.5%. Between them, you have 95% of probability to have the good value. So from the PDF, we have to integrate it in order to have the cumulative distribution function. What is this beast, this strange beast? Is the function which have, if you put x0 as an argument, it will give you the probability of theta to be less than x0. For instance, if I put CDF of 0.5, I have the value. No, if the result of this function is 0.5, it means that the x0 you put is the median value. There is 50% of chance that the real value, the real parameter is below, and 50% of chance that the real parameter is above. So we have to determine what is the bound which will yield 0.025, and what is the other bound, the upper bound, which will give you 0.975. So in other words, you have to invert this CDF. You have to find the CDF minus 1, the inverse CDF. And the inverse CDF will have as an argument 0.025, and will give you what is the bound here, and the same for the other bound. In the case of u equal 2, it's quite simple, because if you integrate the PDF that we have, which is this one, you remember the ones that we have determined. You remember that theta here is x, because we want to know what is the probability for a given x. And it's, the result is quite simple, because it's only exponential of minus c over x. You remember that x is a variable. And this is quite easy to inverse, because the CDF minus 1 of z, you take the log of that, and the log of that, you have, if you take the log of that, you have minus c over x, so you can put x on the other sign, etc. And you have the result which is here, which is only minus c divided by log of z. So if you replace here z by what is interesting for you, 0.25 or 0.975 or 0.5, you will have all the estimates. You will have the bound at 2.9% of probability, the bound of 97.5% of probability. And the result is this one for a square distribution. It's given in terms of the measurement. It's 0.27 times the measurement, because you remember that the measurement c is what you consider as the estimate hat theta, of the parameter. So you have the hat theta parameter, which is between 0.27 xi and 39 xi. So you see it's a wide, very wide uncertainty and very wide error bar. And in this case, you see that what is very interesting in this result is the confidence interval itself. It's not the value of the estimate, because if you choose the median, the mean, or anything, it doesn't really make sense. What makes really sense is the width of the error bar. And I think it's a very important takeaway message to keep in memory. Okay, so I will focus a little bit to this distribution. So it's the distribution of theta knowing xi. It looks like that. So you see that you have a probability density function with a maximum, which is very visible here. but which decrease very, very, very slowly. It's what we call the heavy-tailed distribution. And it means that if I want to plot the results that I obtain, it's not possible on it, because if you have a linear plot, the 95% error bar, it begins approximately here, and it ends, you see the limit of my plot is 10, it is at 40, so it's 4 times this screen, so it's not possible at all, but we can see what is important. You see that here I have the 68% error bar, so it means that you have 16% of probability to be here, 16% of probability to be there, and 34, and here you have the probability 50, 50, the median. But generally we prefer to use the measurement X, which is Xi, which is here, but we saw that it doesn't really matter in this case. So the bounds, of course, at 68% are a little bit more narrow, but not so narrow, because it's 0.5 and 6 approximately. So if you have 1 and more or less from 0.5 to 6, it's still a wide uncertainty domain. If we want to see the 95% error bar, you have to deal with a semi-log X plot. So here we have the log, and you see now that we have the full error bar, and it's still not possible to see exactly what happened here, but we have to imagine that here we have still 2.5% of possibility for the parameter to be. Why is it not possible to see it? Because it's very small, okay, but it's very long. And because it's very long, you have 2.5% of uncertainty. And in order to see that, you are obliged to look at the log-log plot. And here you see that you have something which decreases approximately like 1 over theta square. It is not at all an exponential decreasing like this one. So it means that it's really what we have, an heavy-tailed, the so-called heavy-tailed distribution. The heavy-tailed distribution are a domain in itself in mathematics. There are some statisticians who are specialized in the domain of heavy-tailed distribution. Okay. So what happened in the general case? In the general case, you remember the strange face of the PDF. The PDF is not simple at all, but it's still possible to get the posterior. So from this probability of the measurement knowing the parameter to go to the probability of the parameter knowing the measurement, you just have to multiply by 1 over theta and to normalize. This is quite easy to do. You have that. But what is very difficult is to integrate it first, even with Mathematica. And it's very difficult once you have integrated in order to obtain the CDF. It's very difficult to take the inverse CDF. So generally, it's not possible to do that analytically. But if there is no analytical solution, there is still the possibility, and it's generally what is used, to make a numerical integration. And from this numerical integration, you can have access to the bounds 2.5 or 16% and the median and so on. And you can also compute the mean value. So how does it look like? It looks like that. So you have here the numbers of degrees of freedom, which is in abscissa, and here we have the error bars. So you see that if you have, the example that we use was nu equal 2, but if we use nu equal 1, it's something which appears in the Allen variance plot, because if you do an Allen variance plot, the last point, the most right-hand side plot, dot, is generally the one which obtain if you have a sequence of n data. If you use tau equal to n over 2 and tau 0 over 2, you just have one half of the data minus one half of the other half of the data, you take the square, and you have only one appearance, so you have only 1 degree of freedom. So it's really the last dot, and you see that in this case, you have an error bar which is very, very high, because you have more than 3 orders of magnitude, almost 4 orders of magnitude for 95%. If you are dealing with 68%, generally 68% it's called 1 sigma, but 1 sigma is improper in this case because 1 sigma is only for Gaussian. If we deal with chi-square distribution, it's not at all 1 sigma. So the 68% error bar, you see that it's approximately 2 decades. So it's very, very huge. Of course, you have the possibility to choose the measurement itself, the median, but who cares? There is absolutely no interest to choose one preferentially to the other one, because there are no sense. What has sense is that. For me, you should be aware that the error bars have sense, not the estimate itself. With nu equal 2, you retrieve what you obtain. You see that neither with 1 or 2 degrees of freedom, it's possible to compute the mean value, because the mean value doesn't converge for this sort of distribution. It converges from 3 to the other ones. So at 5, at 10, and so on, you see that you have the mean value. You see also that the mean value is not equal to the median value, which is not equal to the measurement. But when you increase, when you equal 100, for instance, you can consider that they are approximately the same. They all converge to the measurement itself. So the distinction is not very important. Another time, what is important, it's really the error bar, the height of the error bar. And you see, I was about to forget that, which is the main point of my talk, that the error bars are always longer upward than downward. It's particularly visible for a small number of degrees of freedom, but it's still visible up to here. From nu equal 100, you can consider that you have more or less a Gaussian distribution. So in this case, if you, with the algorithm of Greenall and Relay, you obtain a number of degrees of freedom which is more greater or equal to 100, you can consider that you have a Gaussian, and you no longer have to deal with this thing. So no means for 1 and 2 degrees of freedom. If I zoom a little bit here, you see that the convergence is relatively quick, but okay. Last question. Would it be better to take variance or deviation? According to the recommendations I gave you in my previous slide, my previous seminar, I think it's better to use variance, but in this precise case, it's possible to do the job with variance or with distribution, provided the fact that the same computation are possible with deviation, but they are no longer chi-square distributed, they are Rayleigh distributed. And the Rayleigh distribution is another distribution, which is square root of more or less the chi-square distribution, but it's not so easy to get support from software. I think Mathematica, MATLAB, GNU Scientific Library, for all of them, the chi-square distributed is very well tabulated, but not the Rayleigh distribution. So it's, in my opinion, it's easier to use the variance in order to determine what are the error bars. But you say, yes, but my plot will be on deviation and not variance. That's true, but it's not at all difficult. You just have to compute the square root of what you get. And if you compute the square root, or if you shrink your plot, you have exactly the same thing. In order to see that, I present here what happens with the variance, and the same with deviation. It's exactly the same. The only thing which changes is the fact that you have here 100, and now you have 10, but the shape is exactly the same. It doesn't change the shape, it's always the same thing. Okay, so it's time to have the summary of my seminar of today. In order to find a confidence interval around the variance, if you want to make an error bar, whatever the variance is, you have first to use the variance and not the deviation. I already did that. To estimate the equivalent degrees of freedom by using the Greenwald and Riley algorithm. Deduce the PDF from the equivalent degrees of freedom, the PDF of the measurement. Choose an adapted prior, 1 over theta like me or another one. Calculate the posterior PDF. Calculate the CDF, which means the integral of the PDF, and the inverse CDF, generally by numerical integration. And after that, you can compute the bounds of the confidence intervals and calculate the square root in order to plot them on a def plot. And remember, trust the confidence interval, beware the estimate. Sometimes the estimate are not at all informative, it's not significant. You think that you have a measurement, but the measurement is, it doesn't contain any information. What is, the information is really contained in the error bar and not in the estimate. So as a conclusion, I would say that this Bayesian method may be used for all variances, AVAR, MVAR, HVAR, PVAR, and so on. You can invent, for all these variances, we always have chi-square distributed samples. So it works with all of them. This is the algorithm which is used in sigma theta. I don't know if it's used in other, I think it's the only code which uses the Bayesian analysis of the uncertainties. But it doesn't work directly if you have more complicated samples. I mean, for instance, if you have combination of variance, which is the case of the three-corner hat. If you want to make that with a three-corner hat, you no longer have chi-square distributed samples, so you have to search for the distribution of the measurement knowing the parameter, and sometimes it's not so easy. And once you get that, after it's the same problem. You choose a prior and you go on. But you have first to know exactly what is the PDF, the probability density function of the measurement knowing the parameter. Sometimes it's not so easy. So the linear combination of variance is no longer chi-square distributed. So we obtain with Eric and Enrico 2 new Bayesian algorithms, which are KLTG and KLTS. I will detail that in my next topic, my next seminar on April 10th. So remember, in any variance plot, the error bars are always longer upward than downward. And it concludes my talk. Thank you very much for your attention.